Welcome to week 4 of your statistics tutorials. This week we'll be focusing on the regression. Okay, so we have our SPSS window open and we have two different variables here. So let's say in this hypothetical situation we're interested in knowing whether the amount of time spent in your vehicle predicts the number or the amount of mileage you've used. So we have two interval ratio variables here, so we can conduct our regression analysis rather. So to do this, it's pretty straightforward. We click on Analyze Regression, and you're interested in a linear regression. So there's lots of options here. However, we're going to focus on this option. So we click, and actually, sorry, I'll just reset it. So we have a number of different options even within this window for linear regression, but for the purposes of simple regression, we really just need to worry about the first two cells here. So at the top, we want to put our dependent variable. So we had said that mileage would be dependent on the amount of time spent in the car, and then our independent variable would be time right here. So you could proceed right away, however, we do have a few options we need to select. First, actually we don't need anything there. So if we want to click on options, sorry. Okay, sorry. Actually, the only thing I was just looking for the bootstrap and I realized that there's an option there. So what we need to select is this perform bootstrapped option. So, and we want to make sure that it's on the bias corrected accelerated version. So once that's selected, we click OK. There's actually nothing else that you need to select in any of these other options, and you can proceed with the analysis right away. So again, since we're running the bootstrapping, it is going to take a little bit longer, but the bootstrapping is what will give us our confidence intervals. So as we see in the output, we have a number of different tables. So at the top, we just have a list of the variables that were entered. So you can actually conduct a bunch of different simple regressions at once. And as we'll see next week, you can also do multiple regressions. And in this section here, you get a summary of what was done. So in this case, the dependent variable was always mileage. And in the first model we tested, we had time as the independent variable. So what we get here in the first table of the results is the model summary. So you can see here we have the R value, the R square, the adjusted R square, and the standard error of estimate. So for the purposes of this table, we'll just focus on these two right here. So your R is your correlation coefficient, and since we're only looking at two variables, so one independent variable and one dependent variable, this is actually equal to the Pearson correlation that would be conducted or calculated for this relationship. And then the R square, we take that value and square it, and we have that measure of effect size that we've already seen. Next, we have our ANOVA table. So this is where we determine whether the model as a whole, so our linear regression model, is a good fit for our data or not. So as you've seen in class, you have your regression, which also could be called model, residual, and total. And then for each of those, we have a sum of squares, the degrees of freedom, then the mean square, which is degrees of freedom, the sum of square divided by the degrees of freedom. And then the ratio of this divided by this gives us our F statistic. And you can see here that it is 89.185. So if you were to look this up in the table to see if it is significant or not, you would look it up using these degrees of freedom right here, so 1 and 8. So, but SPSS has already done it for us, and we know that this is a significant F value. So what we can conclude here is that the linear relationship we have proposed is appropriate, or more appropriate rather, than just the mean for describing our data. So in the next section here, we move into our coefficients. This is our actual regression equation. So we have two different cells or tables here, and they're basically duplicates of each other. In the first, we have the regular output that SPSS would give, and then we have the additional output that SPSS generated because we asked for our bootstrapped coefficients. So I'll start by explaining this one, but as you'll see in a second there, you won't need both. So what we have here is the output is divided into two different rows. So we have a row for the constant and a row for our independent variable. And for both the constant and the independent variable, we have a b value here. Okay, so that's the actual or parameter or the coefficient that we're going to use, and then the standard error of that coefficient. So already right here we have the two values we need for our equation. So our equation would be y equals the constant, which is 30.312, plus 9.98 times x. So that's the formula. So they're both here. And then you have the standard error there. We discussed in class that the regression equation, or regression, does not provide a standard estimate of that linear relationship, and that if you'd like to know what the standard coefficient is, you need to actually convert your scores into z-scores and then rerun the analysis. Fortunately for us, SPSS actually will do that automatically when you conduct a regression analysis, and will give you the value of the standardized regression coefficient. So you have it here, and notice that there's nothing for the constant. Okay, so we do have the coefficient right here, but nothing there, and that is because in the standardized regression equation, the constant is equal to 0. Okay, so when x equals 0, y also equals 0. And then the next section here, what we have are some t-tests. So we haven't covered t-tests yet in this course. However, you should remember from your last course that a t-test is a mean comparison test, where you compare two means, and if the difference is big enough, you can reject the null hypothesis that the two means are the same and conclude that there is a difference. So what this t-test is reporting is the difference between this value here and 0. Okay, so since we don't, in most cases you don't really care if what your constant is, because it just represents the value of x, or sorry, yeah, the value of y rather, when x is equal to 0. So if this is close to 0 or different to 0, in most cases doesn't matter. However, maybe for the purposes of your research question, you need this value to be different than 0, then you would care about this row, but in most cases you don't, and you're more just concerned with this bottom row here. So what this is a test of whether, or another version of the same test essentially here, is whether the slope, so b here, is significantly different than 0. Because keep in mind, if we had a slope of 0, it would mean that there is no linear relationship. So we want this to be significant, and it'll always match the value here, indicating that this value is not the same as 0. Okay, so we kind of get at the same thing, but when you calculate this by hand, you won't go through the step of getting this. However, SPSS does generate it for you. So then, in the next section, we have a similar table. However, it has been adjusted for our bootstrapping. So what we also have now, and this is the whole reason for running the bootstrapping, is we have the estimate of the confidence intervals. So if we look here, we have the same coefficients there for the constant and the same coefficient for the b, so the parameter multiplied by x, or the slope. And we have now an estimate of the bias and the standard error, which we don't need to worry about. And notice that the significance value has been adjusted slightly for both. However, the one here that matters is still significant. And here's where things get exciting. We now have a 95% confidence interval for the upper and lower values for both the constant and the slope. Okay, so we can see here that we are 95% sure that the true value falls somewhere between 7.38 and 13.77, which is still, above 0 as it is here. So we can be fairly confident that there is a linear relationship between the two variables. Okay, so that's how you look at the output for for the regression. Next week we will talk about running some of the more complex models in regression, so including multiple regressions. I didn't really talk about rechecking the assumptions in SPSS here of this test. If you recall the things that we looked at last week for the correlation analyses, looking at the scatter plot to confirm there's a linear relationship, checking your variables for outliers, etc., would all be part of the steps you would want to do before conducting your regression. However, if you don't remember how to do those, you can watch some of the older videos. Okay, that's all for this week. Oops. Thank you.